we're going to talk about the kernel of a linear transformation. This is related to the null space of a matrix that we saw before. So the definition is the kernel of a linear transformation is the set of all input vectors that have an output vector of 0 using our function. So that is, we're looking for all the points whose output in our function is the 0 vector. So let's look at a couple examples here. What is the kernel of this function that goes from R2 to R2 and takes an input vector xy and spits out an output vector yx? Well, let's think about it. We want the output of the function to be the vector 0, 0, but the output is the vector yx equals 0, 0, and the only time this happens is if both x and y are 0, which means the kernel of my function here is just the 0 vector. There is nothing else that would give an output of 0 in this case. So that's all we have. For the next one, what's the kernel of 0 transformation? So remember, the idea is if you have function from any vector space to any other vector space, the 0 transformation is just the transformation where you get 0 out no matter what x is. So any x at all, the output is going to be the 0 vector. Well, in that case, since kernel is all the things that give 0 out, and everything gives 0 out, then that means the kernel is going to be the entire domain of the function, the entire vector space V. Now these are kind of your two extremes. The smallest kernel you could ever have is just a single vector, and the biggest kernel you could ever have is the entire vector space altogether. The more interesting cases are somewhere in between. So for this next one here, we are looking at the function x comma y that spits out the single number x minus y, and we want to see what is the kernel. So I want to find out when is my answer 0. Now notice in this case I'm just saying 0, not 0, 0, because the output are not two-dimensional vectors. The output are just R numbers, so it's just being 0 here. And what is the output actually? It's x minus y. And so this only is going to happen if y equal to x. And so what that means is the kernel are all the points, or all the vectors on the line y equal to x. So we can write kernel set of all vectors xy where y is equal to x. Again, it's not just a single point. It's also not the entire input. It's just the input that lies on that line. Okay, let's do another one here. Let's look at the kernel of a function that goes from polynomials to real numbers. And the way it does this is it just evaluates the polynomial at the point 0. Okay, so again, we want to solve for when is the output 0 here. Well, that means that if you plug in 0 into the polynomial, you get 0. And since we're talking about quadratic polynomials, we have ax squared plus bx plus c. And if you plug in 0 to that, you get just c. So that means this is the kernel is going to be all the polynomials that do not have a constant. So we'll just put ax squared plus bx, where a and b can be any real numbers. Again, that's not just the 0 vector. It's also not just everything. It's somewhere in between. It's all the polynomials whose constant term is 0. The next theorem here gives us a nice little result that shows us that the things we talked about so far were not a coincidence, that we're getting these specific sets. It turns out the kernel of any linear transformation is always going to be a subspace of the domain. So that's why we got a line here, not like a parabola or something, because if you have the kernel of linear transformation, it has to be a linear subspace, so it's going to be things that are straight, lines and so on. Now, because most kernels are not just a single point or the whole vector space, they're somewhere in between. There's going to be infinitely many answers, but they might not be easy to describe. They might just not be a line y equal to x. So what we'd like to do is, instead of asking you to find the kernel, we're going to ask you to find a basis for the kernel. That's the most common type of problem from this section here. And it's actually not so bad how you do it. You're just solving the equation, ax equal to 0. So you're going to go ahead and write down your augmented matrix here, because we want it to be equal to 0. You're going to do your row operations. In this case, there's really not much to do row operation wise. And then you write down, you've got 2 pivots, you've got 1 free variable. So you're going to write your pivots in terms of the free variable. X minus 2z is 0. Y minus 2z is 0. That means x is 2z. Y is 2z. So then I go ahead and put x, y, z here is 2z, 2z, z. Then you're going to factor out your free variable z and get 2, 2, 1. And whatever vectors you get over here, that is going to be your basis. So in this case, there was 1 free variable, so there was 1 vector. If I had 2 free variables, I would end up with 2 different vectors here, and so on. And that is going to be your basis for your kernel. And the last thing in this video is telling you what the word nullity is. Nullity is just defined as what is the dimension of the kernel. So for the problem we just did, since there's only 1 vector in the basis, the nullity is equal to 1 in that case. Whereas if I had 2 different free variables, the nullity would be 2. And in general, the nullity is going to be the same as the number of free variables that you have in your given matrix.